Okay, this is part 2 of this run through for the Pearson Edexcel linear exam for physics advanced level, paper 2. So it's called Advanced Physics 2. Yeah, so Advanced Physics 2 in the linear has the same content as the International A-level, Unit 5. The year 13 topics are the same. The difference is the advanced physics includes year 12 topics on waves and materials. Well, if you think about it, waves are required for astrophysics, looking at spectra for stars. So it makes sense to link in waves with the year 13 content. So this will also help students preparing for Unit 5 IAL. The Unit 5 exam is next Wednesday, 4th of June, and the IAL, the linear exam, is on 9th of June again next year. Okay, so it's on 9th of June 2023. So it's 2023 run through, and it'll be on 9th of June again in 2025. Okay, so whichever exam you're preparing for, this paper will help you. We did the multiple choice already in section 1, and now I'm going to go through a couple of questions from the structured section, and I'm going to do question 11 and 17 because they both involve waves. Okay, either waves from year 12 or the link between waves in year 12 and topics in year 13. So question 11 first. The photograph shows a string instrument called a cello, being played with a bow. Standing wave forms, okay, on a cello string. So the standing wave is triggered by the frequency of the bow moving across the string, or the vibration of the bow, which creates the standing wave. You've got to deduce whether a thicker string on the cello will produce a higher note or a lower note, higher frequency or a lower frequency. So the equation that you need to be thinking about is the velocity of waves on a string. Yeah, so you're looking for a thicker or a less or a thinner string. So a thicker string will have a higher mu, which is the mass per unit length, which is in this equation. Okay, you have to. They told you what to assume. So we're going to assume each string has the same length, which on a cello they do. Yeah, they're from here, where the nodes are, to the other end where they're roughly the same length, and the tension is the same. So remember, we have to assume certain things to be able to make the theory work. So therefore, a higher mu with a temperature constant, okay, because a thicker string means it has more mass per unit length. So we know the velocity will be smaller because you can see from the equation that velocity is inversely proportional to the square root of the thickness or the mass per unit length of the string. Okay, so since V equals F lambda, and we know for a standing wave that lambda is proportional to the length, and for the fundamental frequency, we know that the lambda is equal to twice the length for the fundamental. Okay, so if V is then proportional to F, if V goes down, then the frequency must go down for the thicker string. Okay, so we know for the thicker string, V does go down, so frequency will go down, so you will have a lower pitch for the thicker string, which intuitively you already know. Yeah. So I think that you need to verbalize it, probably not by putting these arrows like this. You've got to put this into clear English. Okay? So clarity of your communication. But these are the points, and there's the reasoning that I've put down for you. So you've got to practice writing clearly with the correct level of depth and detail to get the marks. The black arrows show, the black ticks show where you get the marks. So that's 4 marks on waves, really from year 12 knowledge. I'm now going to go to question 17, if I can find it. 15. So we can come back and do cosmology in separate videos. Question 17 is this one. Okay, so again, question 17, you see, requires your knowledge of waves from topic 12. Scientists can analyze light from stars that have passed through a diffraction grating. So the main topic from year 12 is diffraction grating. It's a 6 marker. So people doing year 12 can also benefit from seeing this part of this question. Explain the pattern produced when a mixture of blue and red light from the same source, has to be from the same source for it to be coherent. Yeah, so remember, from the same source means that you're going to have a coherent wave source. Because no 2 wave sources with light will be coherent because they're unique. Like everyone has fingerprints, each light source will be producing a different random creation of photonic energy. Okay, so these red and blue light from this single source passes through the diffraction grating together, and then obviously red and blue light have different wavelengths, so it's going to affect what you see. So the key points that you need to put in your answer, which I'll do in green, is interference or superposition. So the waves through the diffraction grating will interfere with each other, and diffraction grating has many waves per millimeter. And when these waves arrive in phase, yeah, the pattern you see will create a bright area. When the path difference between the light arrives with a complete number of wavelengths of difference, okay, the path differences. So bright fringes will seen when you have constructive interference. So these 2 points are linked, okay? Now, because red and blue light diffract differently according to their wavelength, remember the equation is n lambda equals d sine theta. They're going through the same diffraction grating, so d is constant, yeah? And you're going to get different numbers of bright fringes, but they'll be in slightly different positions because the wavelength of red light, for example, is higher. So if red light has the higher wavelength, yes, I don't know how it did that. So when the wavelength is going up, then the angle will also go up. So for red light, the angles will be larger because theta is proportional to sine theta, yeah? And for the blue light, the wavelength is lower, so the angle will be smaller, okay? So going back to the answers and the way you have to verbalize these key points, the diffraction according to their wavelength, red light will diffract more. So the wavelength, because the wavelength of red is greater than the wavelength of blue, according to n lambda equals d sine theta. So you should put all this even in brackets, for example, when you're verbalizing it in slightly padded out form as I'm speaking it. But the central maxima, or the central maximum, because it's singular, will be a mixture of red and blue because they've gone the same length to come to the middle. All the light from all the diffraction grating slits will have traveled equal distance, okay? The red and blue. But for n equals 1, for example, the blue will be closer to the central maxima because the angle is smaller than n equals 1 for the red, because red diffracts at a wider angle, yeah, for the first maxima. And remember, the first maxima will be when there is the path difference n lambda will be equal to 1 lambda, when n is 1. Okay, so this kind of information is all from year 12, and it's a 6-mark question, so you've got to learn how to put it in the correct level of depth and detail in a clear, logical way. And this is how they mark it. So you can see they give you, for your content that I've just pointed out to you, maximum of 4 marks, and then they give you up to 2 marks for how clearly you have reasoned it. So that gives you a final mark of 6 maximum. So this is the content. Waves diffract, waves from different slits interfere. Yeah, so just knowing what interference is. Constructive interference is when the path difference is equal to a whole number of wavelengths. Bright lines will be seen when there's constructive interference. Now, of course, you're going to have a mixture of red and blue light. Yeah, so these 2 points are linked. N lambda equals d sine theta should be mentioned. So to show that the angle is greater for the red light, which has a greater wavelength. Okay? And blue wavelength will be shorter than red. So I think I made all these points, and I think I've explained it clearly. So I think I deserve 6 marks, even with my bullet points. Okay. The next part is now going into an application of waves from year 12. So this is a linkage between year 12 and year 13. A spectrum of visible light emitted by a particular star is shown. So we've done spectra in year 12, and you're going to use them in year 13. So the wavelength is in nanometers, that's 10 to the minus 9. And you can see here's the hydrogen line, the G line for hydrogen, the F line for hydrogen, the B line for magnesium, a D line for sodium, and a C line for hydrogen. So this is what scientists know these lines correspond to. And it says that this is knowledge they're giving you. Light interacts with atoms as it passes through the atmosphere of the star and causes these absorption of the spectral lines, so dark lines. They want you to explain how this leads to the formation of these dark lines within the spectrum. So they want you to explain absorption spectra. Okay? So the key points this time to include is a 4-marker, so a 6-marker followed by a 4-marker, and this is what many students who are good at maths and are studying perhaps in a language where English is, or it's not their primary language, yes, that they struggle sometimes to verbalize it clearly, so you really need to practice. So there are discrete energy levels in all atoms. Okay, you need to mention the word discrete, yeah, and you need to say that photons which are absorbed, so absorbed photons, create electron excitation in atoms, but they only do so if the specific photons, or if the energy of the specific photons, HF, happens to match a difference in energy levels in the atoms, in the atomic levels. So each atom has different energy levels. So for example, that could be the ground state, this could be the second one, this could be the third one, and they get closer and closer as you get close to the top. This could be a fourth one, and so on. So these different energy levels, for example, you can have a delta E here. Sorry, I should have written delta E here. You could have a delta E between those two energy levels. And if a photon comes in, which matches that energy level, then it can be excited by going up that jump. Okay? And then when it comes back down again, it might, for example, emit blue light. Yeah, so this will be an emission. But this bit will be the absorption. It'll absorb it there and then emit it back down again. And the absorption obviously happens first, and that's why those areas that have been shown on the continuous spectrum of a bright object like a star have areas where it's slightly darker. Now, when they emit it, people should ask, well, why doesn't it fill in the black area again? Well, you have to remember that when it emits it, the emission occurs at 360 degrees, so in all directions. But you're looking at it from one direction, so therefore some of the emitted photons, which are equivalent to the absorbed ones, are emitted back into the star. Hope that makes sense. That's a higher level of understanding, which they haven't required for the Mark scheme. You then have to show that you know that the energy level is, so the energy difference level, I should put maybe here, I could have put delta E equals the AHF, which corresponds to HC over lambda. Yeah? So therefore, because they put the answer in wavelengths, so only specific wavelengths of photons are absorbed and create dark lines. And that's why we call them absorption spectra. Formation of dark lines are linked to the absorption of specific frequencies linked to specific energy transitions. That would be a good word to put in, energy transitions. See, it's quite technical, and the vocabulary is key, that you know all the technical terms. So this could also be a good question for year 12 students as well as year 13 students. Hope that makes sense. This question's not finished. Here are the 4 marks that they're looking for. Okay? Discrete energy levels. Photon causes electrons to move to a higher energy level. Yes, or the atom can become excited, by absorbing, and then the photons are only absorbed when the photon energy is equal to the difference between the energy levels. Okay, so transition occurs, and the photon energy depends or is linked to the frequency and wavelength. Either way, they'll give you the marks. So only photons of specific wavelengths are absorbed, thus producing dark lines. Yeah? So there's the 4 marks. Very important thing to prepare, because this question can be repeated in your exams. So the next part of the question is going into astrophysics, which is only in year 13, and this is using Wien's law. So this is the year 13 part, which isn't in year 12, okay? And we've got to be able to draw a graph like this, how the intensity varies with wavelength depending on the temperature of the hot object, in this case a star, okay? We call this black body radiation, yeah? Okay, so the other thing you've got to look at is that it's not a symmetrical bell curve. It's an asymmetric curve, steeper on the left than the right. Okay? Okay, so we're going to have a look at the question now. It tells you the surface temperature of the star is about 5,800 Kelvin, which is like our sun. On the axes below, sketch a graph, like the one we just shown, of the intensity of the radiation on the y-axis against the wavelength of the radiation for this star. Obviously, stars do not just emit one wavelength. They emit a range of wavelength, and the peak wavelength that they're giving off corresponds to temperature, the surface temperature of the luminous object. So the maximum wavelength can then be worked out, as being 0.5, nanometers. I don't know where we got that from. Oh yes, we calculate that. So they want you to put that on the graph to get the final mark. So you use the equation which is given to you on your equation sheet, which if you've been revising, you'll know about it. This is the one I said is called Wien's law. I haven't included the units, for this is the constant value that is in Wien's law. You can work out the units from meters and Kelvin on the right-hand side, so it must be the same on the both sides of the equation. Okay, so once you have got the temperature given to you, you can work out the wavelength and then put that wavelength here to show the detail required for the 3 or 4 marks. So the peak and the fact that you've drawn it the correct shape asymmetrically, the intensity is 0 when the wavelength is 0. So basically there is a 0 point here, but there's a gap here. It doesn't go to 0 like that. It's kind of asymptotic. Okay, finally the 16-mark question, big one, finishes with fusion. Main sequence stars are fusing hydrogen. Explain why main sequence stars do not collapse due to the gravitational forces, because obviously stars are massive. Yes, so nuclear fusion reactions occur in the core. You've got to say that. In main sequence stars, we're talking about hydrogen. Yeah, this releases energy by mass defect, E equals mc squared, which leads to a higher pressure in the core, obviously. This produces an outward force, because obviously you've got a higher pressure. Pressure is force over area. And this balances the inward gravitational force. So it maintains the radius of the star depending on what the pressure at the center is. Okay? And obviously when the pressure drops, when hydrogen runs out, you actually have expansion due to the forces changing inside the center of the star. Okay? All right, well, that takes me to the end of the second video because I wanted to focus it on topics involving waves and astrophysics, so it's beyond waves and astrophysics. And the next one I'll do when I come back after a break. Okay, thanks for watching. Don't forget to like any video that you find useful and make sure you recommend it to any friends who are doing the same exam. If we get a lot of likes and views on these linear run-throughs, I'll continue doing them. Most of the students already subscribed to my channel are doing the international A-level. So also my recommendation, as always, is to watch the IAL exams to practice the topics you need to. And for linear students, there's so much more that you can use. There's the Year 12 content in Units 1 and 2 for IAL, and the Year 13 content will be the content topics in Unit 4 and Unit 5. Okay, so Unit 5 is linked to Linear Advanced Paper 2. Thanks for watching. Catch you next video. Bye for now.